Let's do this. Good morning, everybody, and welcome to this third installment of our series on webinars, discussing what D-Force can do in the mining industry. I am André Veldsman. I currently head up Position XT. We're a global strategic partner to Luna Innovations. Just before we start, maybe just some housekeeping. If you do have any questions, just type it in the question and answer box at the bottom, and we'll get to that in the end. Also, please keep an eye out for our next installment on the 11th of September, and that one would be on safeguarding tailings and high walls. And without further ado, I'll pass over to Herbert. Herbert?
Thank you, Andre, and good morning, everyone that's attending today's webinar. And today's webinar, we're going to be talking about the nervous system for your mind. But let's delve right into this. So the reality is, mine fires represent one of the most dangerous and most challenging risks we deal with in underground mining operations. And given the right circumstances, a mine fire could occur in any location within an active or abandoned section of a mine, and they can quickly grow beyond where we could control them successfully, and in that process threaten the welfare and livelihood of our workforce underground within the mining operation. And if we look at most recent history, mine fires has been quite a leading cause to fatalities within the mining industry globally, within South Africa as well. And looking at the statistics, I think we should do something more into addressing this major risk within mining. Legislatively, there's actually quite a bit of regulations around this within the Mine Health and Safety Act. With words like adequacies of measures, prevent, detect, and combat the start of mine fires. Preventing persons from being exposed to flame, fumes, and smoke. And ultimately, that we need to require an early warning system in all working places due to the significant risk of a fire. And if we look at Regulation 16.1, the adequacy of escape, do we have enough information to know to where our miners can safely evacuate to safety, into a refuge bay or out of the mine? If we look at the current requirements from the DMRE, specifically on the topic of heat stress, we just spoke about worst case scenario. But the reality is miners in deep underground mines are continually exposed to extreme environments, and very hot ones in that. And to be able to effectively monitor the amount of thermal energy our workers are exposed to is paramount. So how can we do better? And as I said with the introduction, let's talk about a nervous system. With our biological nervous system, we can touch and feel, and it converts what we feel into electrical and chemical signals that our brain can understand. And it ultimately allows us to action on our external input, and it allows us to survive. Fiber optic allows us to convert temperature, strain, and acoustic signals into changes within optical signals, which we can interrogate or interpret. And that allows us to monitor and measure these attributes and create control and alert to the potential risks we are monitoring within our mines. It further allows us to put distributed sensing throughout the entire mine-wide monitoring, where a single fiber optic cable with various cores ultimately becomes one very long sensor, and every part of that sensor being a thermocouple, a strain gauge, and a microphone or accelerometer, and every part thereof through that entire mine. And we can sense and measure these attributes. So how does this work? If we think in the most basic application where we have existing infrastructure throughout our mine, in this case, existing fiber optic communication infrastructure, and we take a spare core within that fiber optic infrastructure, and we would add our temperature sensing interrogator unit to it. We turn that infrastructure into a sensor, and that sensor allows us to continually measure the temperature profile along that entire fiber optic cable with very high resolution. And in this case, I'm simulating a hotspot on a power cable where, as you can see, we can visualize the temperature profile along that fiber optic cable. We can see the exact temperature at that point. And every 8 seconds or so, we've got an updated temperature profile throughout that entire mine along that infrastructure. We can also send various fiber optic cables on at the same time. And in this case, let's say we have fiber optics now in different haulages. And here we can continually measure the temperature profile along each of them. And we can very accurately measure the areas of increased heat, load, or thermal energy. And we can visualize that information within a control room environment and alert the operation to a potential ventilation issue and safety, occupational safety risk. We, however, have various different technologies using fiber optic sensing. We have temperature sensing systems that we can potentially sense up to 100 kilometers per channel and up to 16 channels. We have strain systems where we can measure strain or stress along the fiber optic cable. We have acoustic sensing systems where we can measure vibration. We can measure eddies and airflow, any turbulent flow, and very high sensitivity, short range, but very high resolution sensing systems as well. So how does fiber optics work? If we would think about a bottle of water and we would relate that little bottle of water to the fiber optic core, the silica fiber optic core, if we heat the water, the molecules become more active. If we cool it, the molecules become less active until the water is frozen. Now, if we would take a flashlight and we shine the flashlight through the water and we keep the bottle really still, the light just passes through. But if we shake it around, the bottle starts glowing. Now, that's the light reflecting at these molecules bouncing around and creating reflection or backscatter within that bottle of water. Now, the same happens within the silica glass fiber optic core. We heat it, the molecules become more active. We continually shine a laser through the fiber optic cable. Now, this laser light bounces against these active molecules, creating reflection or backscatter. The intensity of the backscatter integrated is our temperature measurement, and the frequency of the light is the distance within the fiber optic cable, think like radar. And we literally tune into each of the radio stations and we see what's the backscatter or reflection at every point along the fiber optic cable. And we then output that as a temperature profile along the entire fiber optic cable. So the fiber optic cable is the temperature sensor itself. And we can go and break that down into thousands of zones. And within that zone, we know exactly where that point of thermal energy is. These systems are fully FM, UL, PDS certified for fire detection application. And additionally, we have the option for IATF or EAC certification within the coal mining or confined space environment where we have explosive dust or gaseous environments. And we have various systems. The temperature fire detection certified systems we have options up to 14 kilometers per channel, and where fire certification is not required, we have up to 70 kilometers per channel. And we can have systems with resolutions down to 25 centimeters and a temperature resolution down to 0.01 degrees Celsius. Now, for every single channel on this box, and let's say we have 4 channels, we can configure 1,000 zones. Now, each of these zones, we can configure 5 unique pre-alarm and 5 unique alarm criteria. And I'll go a bit into a bit more depth with that just now. Fully integratable, up to 104 digital outputs, Modbus TCP IP, LAN, DNP3 to interface with the current ventilation, SCADA, control systems within the mine. Now, with the alarm parameter set, we can create really unique alarms throughout the entire mine. As this fiber optic cable now runs past different assets or equipment, we can set up maximum temperature or minimum temperature alarms, hotspots alarms, that's the total temperature over the average temperature of the section. So that would be really interesting within an MPC where the fiber runs past the transformer or a potentially hot asset. And if we can see that that area, there's a point where it's hotter than it should be, let's go and investigate. Maximum temperatures would be typically in the throughout the working sections of the mine. If we go say, over 38 degrees Celsius, we're already in alarm. If we go over 35, we're in pre-alarm condition set. And then out of a fire detection perspective, we can use rate of rise alarms. If we see that the temperature at this crosscut is suddenly going up faster, or there's a rapid change in temperature within that environment, we can create a pre-alarm condition to go and investigate. And if that keeps on continuing, that can go into an alarm, indicating exactly where that point of thermal energy is. Now, all these alarm parameter sets work together to create a unique alarm grouping. Now, we can set up different alarms for the cold air section, the exhaust section, for every, depending on the air movement through a haulage, within an electrical substation, within a refuge chamber. We can set up unique monitoring parameters for each of those sections throughout the mine. We spoke a little bit about the sensor cable. This is its construction. We have 4 fiber optic cores in there, stainless steel tube, stainless steel wire armoring, fully fire certified, extremely robust. Now, our interrogated units can interrogate data theoretically from minus 180 to plus 1000. This sensor cable will be comfortably minus 50 to plus 150 and carry certification for explosive dust and gas environments. One of the major benefits of fiber optics above any other sensing technology is that it requires very little to no maintenance. It's immune to vibration, dirt, dust, smoke, radiation, electromagnetic field, corrosion. We can run this literally around a transformer and it won't. And we do, however, do that to monitor their temperatures without affecting our ability to measure. And I always use this argument. And if the tunnel would flood, we would know what the water temperature is. So really, really robust sensor that runs throughout the mine. And we'll share a bit more information on the testing we've done at Toppersbos during the years as well. As I said, 2 single mode and 2 multi-mode cores, depending on the distances we want to measure. These cables are fully fire survival rating, pH 90 rated. And this allows us to also communicate emergency signals through this fiber optic cable. It is approved for that application as well. This is a typical connection installation. This is a 2-channel system. We can have up to 4 channels on the fire certification. If fire certification is not important, we can have up to 16 channels. In most safety applications, we do install in a loop configuration. It could also be installed single-endedly. We can have up to 104 digital outputs to interface with SCADA, PLC, and emergency trip circuits. A dedicated Ethernet port for our database and visualization software, dedicated port for Modbus or industrial protocols, and very little power consumption, about 3 amps to 24 volt DC. On the sensor cable, if we have a fiber break, we know exactly where the cable is broken to go splice it back up. And being a normal single mode and multi-mode fiber optic cable, it's a normal fusion splice, nothing special in regards to the repairs. And if the fiber is broken, the controller ignores about 20 meters either side the fiber break for bad reflections within the cable. And this allows us to, still have kilometers and kilometers of sensing and just splice it back up and the full system is operational. And so we've alluded to this before, that one of the main applications within mining in tunnel environments would be fire detection, where we would run this fiber through the existing infrastructure. And what this allows us is to detect the exact location of the fire, the speed and direction of the movement of the fire, as well as the hot gases. And that ultimately enabling better response to it, to the first responder and the proto team, knowing exactly what the temperature is, in which direction it's moving, what's the cold air side, so we can monitor it with traditional technologies very much. And we know what is our concentration at a specific point with distributed sensing. We know where the temperature is along the entire fiber optic cable. So we have a lot more information to deal with. All this data is saved in the database software. So we can go post-incident investigation. We can see exactly where the fire started, the temperatures, the movement of the gases along the fiber optic cable, and the thermal energies. And as I said, compared to traditional ways of thinking, no dead spot. Wherever the fiber optic cable is running, we are monitoring. This leads then to, now that we have all this data, it also leads to ventilation efficiency monitoring. Now that every 8 seconds, we've got an updated temperature profile along the entire fiber optic cable. And if we add in the data of existing instrumentation, we can really build a more accurate model of the air movement through our underground mining environment. With the addition of acoustic sensing system, we could also potentially measure the orifice noise throughout the geologist to work out air velocity movement. And combined with temperature and acoustics, with traditional technology, we can really measure the ventilation efficiency. So through the years, we've done quite a bit of testing. Most recently, end of last year at Klokkerpoort, where we've installed the fiber optic sensor cable within this test mine ventilation tunnel. So you can see the sensor cable running on the ceiling there, on the hanging wall within that section. And within this test, we simulated a fire within a mining machine, an LHD. So there we immediately, obviously, alarms to rate of rise. We can see the temperature profile along the entire fiber optic cable and the air movement. And we can see in which direction the hot gases are and is moving, and the smoke. We can identify exactly where that fire is. We can see the actual temperatures along the fiber optic cable. We know exactly which zones or which sections within that mine. And with the extinguishing system activated, let's say within the machine, we can see how dramatically that section within the mine is cooling off. And we can visualize that information, allowing us so much more information than traditional technologies allows. And all this data is stored within that database and is communicatable to third-party systems to enhance our data integrity. Many years ago, the collieries asked if this will survive an explosion within an underground coal mine. So we again bent the copper post and we stuck the fiber into the tunnel, the research tunnel, and we tried blowing it up. And quite successfully, we measured the temperature after the explosion within the tunnel. We originally were concerned that the shockwave would potentially damage the fiber optic cable, but we ended up doing a couple of tests on it. The cable was good. We did even bigger tests. And obviously that's a lot hotter. And we did about 4 of them and decided we only have to survive 1 explosion. So the reality is the sensor cable is extremely robust and ideally suited for in that environment. But mines are just tunnels. And the reality is that this technology has been used successfully within other industries and within the transport sector for decades already. And we have done over 250 tunnels, being rail and motorway tunnels throughout globally. And this technology has actually been proven quite successfully. I've got 2 samples here of 2 major fires within Europe, where this one in Switzerland, where there was a major fire, and our system was installed within that tunnel. And to give an idea, within this case, we measured exactly the location of the fire. It went up to 619 degrees Celsius. We continually, throughout that fire event, monitored the temperature. You can see our sensor cable was directly within this fire, and it was still fully operational. And here's a second fire within a tunnel. And this tunnel was a little smaller vehicle. It burned was about 530 degrees Celsius. Again, we knew exactly the temperature distribution through the tunnel, the exact location thereof. And with this vehicle, it burned. And again, our sensor cable survives the fire incident, allowing real-time continuous data to the control room, the proto team, first responders, allowing us so much more information to manage this incident underground and keep the workforce ultimately safe. This is my presentation for today on a nervous system for your underground mine. Keep in mind that ultimately fiber optics allows us to continually measure the temperature throughout the entire mine. And we can use that data for fire detection, for heat stress monitoring, for ventilation efficiency, and integrate that with current third-party systems, SCADA, control, and ultimately assist with this whole drive in mining to get to ventilation on demand. We have some upcoming webinars for pipeline leak detection and security monitoring, as well as strata and rock stability and block caving using fiber optic sensing. So have a look out on LinkedIn and the SIM calendar, and please mark this. Any questions?
Okay, yes, there is some questions there, Herbert. Thank you for that. Very insightful. Okay, how does DFOS maintain accuracy in temperature and airflow monitoring in the presence of high dust levels and other environmental interferences common in mining operations?
So fiber optic sensing in general is completely unaffected by external dust or moisture within the environment, because we are interrogating the temperature change caused onto the fiber optic cable. It will not drift. It will not lose its accuracy. Doesn't matter how dirty or dusty the environment is.
Okay, next question. This is for ventilation, obviously. Can the technology differentiate between different types of failures, such as blockages versus fan malfunctions?
Because of our location accuracy along the fiber optic cable, we can set up very unique alarm parameter set. So sections where we run next to a fan, we could literally wrap this fiber around the fan and monitor the fan's actual operational temperature. So if the fan is not running, it's colder, and we can alert to that, as well as the temperature distribution directly after that fan. Now, the same goes for, let's say, blockages or ventilation fields that either open or close. We know what the temperature should be, and if there's any deviation from what is expected, we can create an alert and alarm to that based on our alarm parameters.
Thank you. Okay, and next one. How does the calibration affect the accuracy of fire detection over time? Does it need to be recalibrated after some time?
Unlike traditional temperature sensing systems, fiber optic does not require recalibration. We know what the performance is of a specific fiber optic cable and how that cable reacts to changes in temperature within the backscatter profile of that fiber optic cable. And that, however, does not change through the lifespan of that fiber optic cable. With traditional sensing technologies, where the material or the metal itself weakens, that needs to get recalibrated frequently. We do not have those limitations.
Okay, sorry, I see, Piet, you have your hand up. Maybe, I don't think you've got rights to speak in this session. Maybe just type the questions in the Q&A box, if you don't mind. Okay, how does DFOS integrate with automated ventilation control systems to adjust airflow dynamically based on real-time data? Could you describe the feedback loop involved?
So every zone that we can create, and we can create thousands of them, has associated to it about 7 protocol tags or Modbus TCP IP tags. Now, within that tags, we have the maximum, average, and minimum temperatures of every single zone. Every single section along that fiber has a address data point, analog data point. All these analog data points can feed into SCADA control systems or ventilation control systems as a physical 4 to 20 milliamp analog sensor would have. And that will then form part of the control philosophy within that system.
Okay. What are the power and communication requirements for a DFOS network in a mine, and how does the system ensure continuous operating during power outages or network failures?
Being 24-volt DC, the system's typically connected to a DC UPS supply, and the size of the DC UPS or the batteries is determined how many hours we want to keep the system up, keeping in mind that we use only about 70 watts of power. It's quite easy to keep these systems powered by DC infrastructure for days on end. Out of a communication perspective, we do require a fiber optic network from the underground location, being it an e-house or substation underground in the mine, to then communicate the signals or the information from the box to a virtual server or server environment that runs our visualization and database software.
Okay. How does DFOS handle false positives, such as detecting heat sources that aren't actual fires? Is there a filtering or verification process in place?
Being a temperature sensing system, and we're ultimately measuring the absolute temperature of our environment. So it's unlikely that we would classify something as a fire event if it's not. And that's purely based on how those incidences react thermally. We do want some, let's say, early pre-alarm conditions to fine-tune our earliest potential alarm criteria. But we do have dedicated, approved EN and UL certified alarm criteria set for fire detection. And those alarm criteria will only activate if it's an actual fire.
Okay, so I think this one is maybe taking aim the next one at some of your other products, and I think the answer is for strain as well. What is the maximum, the minimum spatial resolution for temperature sensors and strain sensors for Luna products in general? I think that might be a structural thing going on there.
It depends on application. We could go down to 10 centimeter resolution for within the standard TTS product. Within the other T systems, we have down to millimeter, 1.6 millimeter resolution on fiber optic cable. But up to 3 meters, let's say, resolution, let's say on a 14 kilometer system, we will have 3 meter spatial resolution.
Okay. What would the impact of a stationary diesel engine be on temperature sensing? Would it be up to a control room operator to distinguish between a small mine fire and a diesel engine?
We would, however, see a small rate of change in temperature within that environment where we potentially have really hot gases that exhaust directly onto our fiber optic cable. Keep in mind that the spread of that gas will only affect a very short distance along the fiber optic cable. We would potentially create a pre-alarm condition set of such an incident. But out of a fire criteria perspective, the amount of cable exposed to the change in temperature is not significant in that case to be seen as a small fire. Just how, due to the amount of thermal energy that a fire releases against the exhaust gases from a diesel machine.
Okay, and you also have that baseline so that you kind of know what is on there, and if anything builds on top of that, then you can even wrap the cable around the engine, the diesel engine, the engine, to see if it's vibrating or running or anything wrong with it.
Yes, what I do want to add even above that is that out of a heat stress monitoring perspective, because we're continually measuring the temperature within that section of the mine, wherever the fiber optic cable is running in all those sections. But if we have too many machines in that section and the temperature starts rising and it overcomes what the efficiency, what the ventilation has to offer, we can obviously create an alarm to that and saying that this area is starting to heat up faster than it's supposed to, and we are reaching certain predefined thresholds, to indicate that we have a problem within this section. Unrelated to fire, more related to heat stress or environmental monitoring.
Okay, and then how susceptible are the fiber optic cables to physical damage from fall of ground?
It's a really interesting question. So, out of if the hanging wall falls in, the fiber optic cable would get severed. Out of most safety systems, we run in a loop redundancy. So ideally, if it's installed in that fashion, we would know exactly where the fiber is broken, but it will ignore that section of the affected fiber, and we will sense up to the point of failure and around through a different haulage to the other side. If it was a single-ended run, we would ultimately send to the point of, let's say, cable failure, in this case, of fall of ground. Just for interest sake, if we would have a strain system connected to that same fiber optic cable with the temperature system, we would be able to measure the change in strain along that fiber. So as there's ground movement within the hanging wall, before we have a fall of ground, we would already see a rapid change in strain of force applies to the fiber optic cable, giving us the ability to alert or alarm to that incident.
Yeah, so please keep an eye out for one of our presentations on that for Rockmass strain, and also a little bit of that in the tailings section. Okay, simple focus. Okay, is the sensor field bus independent, or you only use the Modbus, or do you only use Modbus?
We do not have field bus at the moment. We have Modbus, DNP3, and LON. We do run it through a middleware server if we need Profibus or field bus outputs. So there is a solution around that.
Okay. How do you comply with the new mandatory guideline on quality assurance program for a system of occupational hygiene and ventilation engineering measurements, which was signed off by the Chief Inspector of Mines on that was this month, the beginning of this month? Yeah. Especially on section 8.2.3.1. I'm not sure if you've seen that.
No, I will have to have a look at that specific document. I haven't read it, so I don't want to comment on it. But on the quality assurance, I want to add the following on the equipment.
Okay, so that's a follow-up.
Yeah, that would be an interesting. But I just want to talk about quality assurance in general on the equipment, because I'm not familiar with. I have not yet read that specific requirement. The equipment goes through an extensive factory acceptance test. The output and the software and the systems are sold to the equipment themselves carry fire certification lists and goes through extensive testing and batch testing to keep those certification levels. The environment itself is a German manufactured, with every single ISO quality management system in place. And these systems actually carry Telco certification for nuclear installations. So out of a quality assurance perspective, there is various protocols in place to ensure that this equipment is stable and reliable. And with that, this equipment is tested with a mean time between failure of 45 years. So in that regard, this box will outlast any of us within mining.
Okay. I was about to say I'm not that old, but I am. Okay. It's a follow-up on the previous one. So in ultra deep mines, the depth is an issue for the BP and air density. Will you be able to calibrate it yearly at the installation site as per the new mandatory COP?
Yes, because calibration for us would really be just reference checking. We do not have to take out the equipment and send it back for recalibration. Because we are measuring the absolute temperature along the fiber, we do have a protocol in place where there's reference points along the installation, which we do verification checking and see that we are within a certain percentage of the actual ambient temperature compared to what the fiber optic cable is measuring. We do have the capability within the software to then adjust the threshold, but in general, yes, we would be able to calibrate on site.
Excellent. That was it. Then just lastly, Palesa, if you can just put up that questionnaire. Guys, if you want us to contact you to discuss your specific needs, you can just indicate so right here. And then from my side, thanks for joining this webinar. But thanks for doing this presentation. It is always great to have you. Thank you, everyone.
It's a pleasure. Thank you.
Great. And that's it.